This lesson is about resonance and resonant frequency. If you were to Google resonant frequency, you would probably get a lot of information about sound and sound waves. But AC power is also a waveform, and so we can talk about resonance within an AC power supply or an AC circuit as well. So what does it mean to say that our circuit is resonant? Quite simply, it means that XL equals XC. So the amount of inductance in our circuit, or inductive reactance, and the amount of capacitive reactance in our circuit are exactly the same, and they perfectly cancel each other out, leaving us only with our value of R for our value of Z. So the impedance in the circuit is only whatever resistance we have in the circuit, because the reactance has canceled itself out. The inductive reactance and the capacitive reactance have perfectly canceled each other out. So we don't have a triangle to build. Okay, our power factor is equal to 1, our angle is equal to 0. Okay, now at first glance you might think, and from the conversations we've had, you might come to the conclusion that this seems like a good idea. Because we have said that when we looked at the inductive circuit, the series RL circuit, we talked about the fact that this is the true power, which is the power that we use, and this is the apparent power, which is the power that we pay for. That's the demand on the power supply. So it felt very inefficient, and we thought, oh man, that's when this is a large angle and we have a small power factor, that seems like a bad thing. And that thinking is not wrong, but when we try to reduce the size of that angle by adding a capacitor, once we put a capacitor in here, so this is our XL, once we added some XC, and we ended up having a new hypotenuse in a right angle triangle, which was shorter, that felt like a good thing. And it is. It absolutely is. Okay? But we don't want to add so much capacitance to our circuit that we end up in the situation where a power factor equals 0. Okay? We'll look at that in just a moment. But I want to finish the thought about resonant frequency before we move on to the additional conversation about pros and cons of resonance. There's two different ways that our circuit can become resonant. One is kind of what I was just suggesting there, is we have an inductive circuit, so we've got a circuit that has a motor connected to it, an RL circuit, and then we add a capacitor to it, and it becomes an RLC circuit. And by adding the capacitance, we reduce the amount of inductive reactance, and we reduce the angle of our triangle. Okay, and that is something that we definitely do. We're going to talk more about that when we get into the parallel circuits, because we do that on purpose, but we are connecting those capacitors in parallel, not in series. So we'll have more about that conversation soon. The other way, however, that we could approach resonance is through the frequency of the power supply. So remember, what does XL equal? XL is equal to 2 pi FL. So as F increases, XL increases. All right, the frequency and the inductive reactance are directly proportional. Okay, so if I were to put that on a chart, if this is frequency, and I'm going to use green to represent XL, as the frequency increases, so does the inductive reactance in our circuit. Okay? What about XC? XC is equal to the inverse of 2 pi FC. So the inverse of 2 pi FC, which means now the capacitive reactance is inversely proportional to the frequency. So as the frequency increases, XL actually decreases. So if I use my red to finish this thought, here's XC. As the frequency increases, XC decreases. So resonance occurs, and the resonant frequency occurs at that point where those two lines cross. Okay, that is the frequency at which this particular RLC circuit will be resonant, when XL is equal to XC and the power factor is equal to 1. Okay, there's a handout that I put on Blackboard that goes through the algebra, and we can actually calculate this. We can take XL equals XC, and substitute XL for what XL equals, 2 pi FL, and substitute what XC equals, inverse of 2 pi FC, and with that equation we can then do the algebra and we can isolate it so that F equals, and it's a big ugly piece of math. Okay? We're not going to worry about doing that math and crunching those numbers, but understand that this is true for any RLC circuit, okay, where we have an inductor and a capacitor connected in the same circuit. There would be a frequency at which that circuit would be resonant. Okay? Now, I said that we don't really want that to happen. Why not? The issue is about the amount of current that's going to flow in the circuit. Okay? So what does current equal? Current is equal to, this is Ohm's law, going way back here for a second, the applied voltage divided by the impedance in the circuit. Okay? Remember, whatever that value of R is, and then we have XC and XL, and we're talking about the resonance situation. So XL and XC are equal to each other, and all we're left with in the circuit is R. So Z will be whatever R is. Okay, there's also a handout about a conversation about quality, and a higher quality inductor and a higher quality capacitor means that we have a very small value for R. Okay, so if we have really high quality devices in our circuit, we have a circuit which has very little R, very little resistance. Okay, and so the result is this. If we look at the amount of current flowing through our circuit as the frequency in our circuit changes, okay, and let's say that somewhere there is our frequency which is resonant, there's our resonant frequency, our current is going to be impeded by the impedance, which when not at resonance is going to include some reactance. But at the moment that we hit resonance, we have only R to inhibit the flow of current through our circuit. And so the current looks like this. And the result is a spike in current through our circuit at resonance. Okay, and so this is why actually having a resonant circuit is undesirable. This is when it's in series. Connected in series, we see a spike in current at resonance. We'll have the same conversation again with a parallel circuit once we've gone through the process of doing the math, drawing the triangles, and all of that. And so that's what's going to come next. The next lesson, we're done with the series circuits now. We're going to move on, and the next lesson will be about parallel circuits.